Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries. We are on day 25 of our hashtag 30 Days of Code Challenge with Educative. Now today's problem is longest common suffix queries. Let's get into it.
Today, we're tackling a problem that looks brutally expensive at first glance, but becomes elegant once you see the pattern. This is longest common suffix queries from LeetCode 3131. And the key insight is simple, but powerful. You can turn any suffix matching problem into a prefix matching problem by reversing the strings. Once you do that, you can use a trie to collapse what would be an O of Q times N times L squared brute force into a clean, scalable solution. Let's break it down. Here's what we're given. We have two lists, words container and words query. Words container is a list of candidate strings. Words query is a list of query strings. For each query word, we need to find the longest common suffix it shares with any word in the container. If multiple container words tie for the longest suffix, we choose the shortest word. If there's still a tie, we choose the word that appears earliest in words container. Then we return the index of that word. That's the full problem. Let's walk through an example. Words container equals, from left to right in the array, ABCD, BCD, XBCD. Words query equals, from left to right in the array, CD, BCD, XYZ. The output is 1, 1, 1 from left to right in the output array. Why? For the query CD, it matches all three container words with a suffix of length 2. The shortest container word is BCD at index 1. For the query BCD, same story. It matches all three, and the shortest is BCD at index 1. For the query XYZ, there's no shared suffix with any container word, so the longest common suffix is the empty string, which all words share. The shortest container word is still BCD at index 1, so the output is, from left to right in the output array, 1, 1, 1. The naive approach is straightforward but expansive. For every query, you compare it with every container word. For each comparison, you check the longest common suffix character by character from the end. You track the best match so far based on suffix length, word length, and index. The cost is O of Q times N times L comparisons, where each comparison can take up to O of L time. So the worst case here, that's O of Q times N times L squared. That's unusable for large inputs. Here's the breakthrough insight. A suffix of a string becomes a prefix of the reversed string. Let me show you an example. The string ABCD ends with the suffix BCD. If we reverse ABCD, we get DCBA. If we reverse the suffix BCD, we get DCB. Now, DCB is a prefix of DCBA. So instead of doing suffix matching on the original strings, we can do prefix matching on the reverse strings. And prefix matching is exactly what tries are built for. Tries excel at three things. First, prefix search. They let you efficiently find all words that start with a given prefix. Second, fast character by character traversal. You walk down the trie one character at a time. Third, storing multiple overlapping paths efficiently. Words that share prefixes share trie nodes. So here's the strategy. We reverse all the container words and insert them into a trie. Then, for each reversed query, we walk down the trie, count how many characters match, and collect the container indices stored at each node. The trie nodes store metadata that lets us apply the tie-breaking rules instantly. Each trie node stores 3 things. First, children, which is a dictionary mapping each character to the next trie node. Second, best_length, which is the smallest length among all the words that pass through this node. Third, best_index, which is the earliest index among the words with that smallest length. This lets us resolve the tie-breaking rules in constant time as we walk the trie. Just to contrast, here's what the naive approach looks like in pseudocode. For each query k, you initialize best_suffix_len to -1 and best_index to -1. Then, for each word w in word's container, you compute the longest common suffix length. If the suffix length is better than the current best, you update it. If it ties, you apply the tie-breaking rules, shortest word, then earliest index. This works, but the complexity is O of q times n times L squared, which is way too slow. Here's the optimized approach in 3 steps. Step 1, reverse all the container words. Step 2, insert them into a trie, updating best_len and best_index at each node. Step 3, for each query, reverse the query. Walk down the trie as far as possible, and the deepest node you reach gives you the answer. The deepest node tells you the longest suffix length, the smallest container word length, and the earliest container index, all in one traversal. Here's how we build the trie. For each word in word's container, we reverse it. Then, we walk down the trie, creating new nodes as needed. At each node, we update best_len and best_index. If the current word's length is smaller than the node's best_len, we update both best_len and best_index. If the lengths are equal, we update best_index to be the minimum of the current best_index and the new index. This ensures that every node stores the best answer for all words that pass through it. Here's how we query the trie. We reverse the query string. We start at the root and initialize the answer to root.best_index. This handles the case where the query shares no suffix with any container word, so the longest common suffix is the empty string. Then, for each character in the reversed query, we check if it exists in the current node's children. If it doesn't, we break out of the loop. If it does, we move to that child node and update the answer to that node's best_index. When the loop finishes, we return the answer. Here's the complete Python solution. We define a trie node class with children, best_len initialized to infinity, and best_index initialized to -1. In the main solution, we build the trie by iterating over word's container. For each word, we reverse it. Then walk down the trie, creating nodes as needed. At each node, we update the best_len and best_index based on the current word's length and index. Then we process the queries. For each query, we reverse it, walk down the trie, and track the best_index as we go. We append the final best_index to the answer list. At the end, we return the answer list. Let's walk through a concrete example. Words container equals from left to right in the array ABCD, BCD, XBCD. After reversing, we get DCBA, DCB, and DCBX. We insert these into the trie. DCBA creates a path D to C to B to A from top to bottom. DCB reuses DCB and stops there. DCBX reuses D to C to B and adds X at the bottom. Now, for the query CD, we reverse it to get DC. We walk the trie. First we match D, then we match C. At the node for C, best underscore index is 1 because BCD is the shortest word that passes through this node. So the output is 1. Let's talk about complexity. Building the trie takes O of n times L, where n is the number of container words and L is the maximum word length. Each query takes O of L because we walk down the trie for at most L characters. So the total time complexity is O of n plus Q times L, where Q is the number of queries. This is a huge improvement over the naive O of Q times N times L squared approach. This problem isn't really about tries. It's about transforming suffix problems into prefix problems. Once you make that transformation, the trie does the heavy lifting for you. This pattern generalizes to many other domains: reverse lookup, streaming suffixes, auto-suggest on word endings, DNA suffix search, file extension matching. Anytime you're dealing with suffixes, ask yourself, can I reverse the strings and turn this into a prefix problem? Here are the key takeaways. First, suffix matching becomes prefix matching when you reverse the strings. Second, trie nodes can store metadata to handle tie-breaking rules efficiently. Third, query time becomes linear in word length, which is a massive speed improvement. Fourth, this optimization is critical for large data sets. And fifth, this is your third trie problem in this challenge. You're solidly in mastery territory now.
And that's a wrap of day 25 of our hashtag 30 Days of Code challenge with Educative. If you like this video, like it down below, share it with a friend, subscribe to our YouTube channel, and we hope to see you next time. Bye!